So 5.2. If you look at this and you say, weren't we just studying polynomials in 5.1? Absolutely, we were. So far, what we know about the polynomials is if we check out the degree and we check out the leading coefficient, we can know the end behavior. We don't necessarily know about the guts of the polynomial because we don't get to see the middle part of it. What we see is what's going to happen as we go to the left forever and the right forever. So today what we need to do is to start to analyze our polynomials, and that includes analyzing the factored form of the polynomial. Here's why. That's how we find the zeros. So not only are we going to know, hey, it's doing this on one end and this on the other end, but we're also going to start to put some of those middle pieces together so that you don't necessarily have to grab a graphing calculator for everything. You know, we'll know, here's the end behavior, here's where it hits the x-axis. Oh, we actually could see how it would do this. But like I said, we're still going to have to grab the graphing calculator for those local maxes and local mins. And that just makes me think if somebody doesn't have a graphing calculator with them today, I better grab some. How many do I need? 2, 3 of them? Try Zoom 6. Let's try Zoom 6. It just wants you back to the standard window. That's just said that I'm not doing nothing until you get back to that. Alrighty. Eventually, and let's see. I don't think we got to this first hour. We're going to write polynomial functions from S0. So we probably won't get that far today, but we'll wait and see. And down here it says, if p of x is a polynomial function, the solutions of the related polynomial equation, where we set it equal to 0, those are, of course, the zeros of the function. And we've talked about this before. The zeros, Jake, put the book away. The zeros, the solutions, the roots, the x-intercepts, they're the same number. It's just we're using them for something different. We're using them to describe a different topic in mathematics. That's why they had all these names. So finding the zeros helps you factor the polynomials. You can do that educated cheat of working backwards once you know what those zeros are. And graph the function. I mean, that's what we're really after here. In Algebra 2, it's all about taking what you see that's algebraic and changing it into a visual for yourself. How can I make this happen? Because what we want for you is to be able to take a class like this and then be able to work in computer programming. And maybe you become an engineer and you're working at an amusement park and they're trying to design a new roller coaster and they want it to show up on the computer so they can show people what it's going to look like. And you could say, I know how to do that. You know, you could put all the pieces together and make it happen. Or maybe it's some kind of new age gaming chair. You see those coming out now for the holidays. We can do that. I mean, that is not an impossibility. We have enough algebra background that after today we'll be able to say, well, this is no big deal. I got a horizontal line here and I just need to make a cubic to make this curve show up from here to here. Now, how do we know if it's a cubic, a quartic, whatever it is we want to use? We would look at the number of turning points, we would look at the end behavior, and in fact, this one would be quartic. We'd use a quartic with a negative leading coefficient because that would make our end behavior look like this. And there are 1, 2, 3 turning points. And remember from yesterday that that's degree minus 1. So we could use a quartic to get this to show up. The only thing we would need a little experience with in a computer programming class would be to tell the computer we only want it from here to here. That would be the only piece we're missing, and that's the easiest piece of the whole thing. So this course especially gets you so ready for that kind of stuff. And there's a lot of money to be made in engineering. So we're going to graph that function. And of course, sometimes we're going to need this to be the answer to something. We're going to solve it. I always think back to my husband had a friend in high school who was maybe 4 or 5 years younger than him because he lived in the neighborhood. And this guy was one of those guys that didn't really take high school too seriously. You know, his 9th and 10th grade year, he's getting into trouble. The police knew his car and they followed him around, you know, that kind of thing. But when he got to be a junior and a senior, he decided, you know, I want to make something of my life, and he turned his life around. And he has actually been on magazine covers for aeronautical engineering now over these past couple of years. His starting wage at his first job, $130,000 a year. And when they wanted to keep him, they said, you need to get a master's degree. And he said, I have a life too. You know, I got a house payment and everything else. And they said, oh, don't you worry about that. We'll pay for it, and we'll pay you while you go to college. So they sent him to Purdue University and paid for him to get his master's degree. And like I said, he was voted the third best aeronautical engineer in the United States, and got his name plastered on the cover of some kind of airline magazine, you know, and he works for Delta. So those jobs are out there. And one of the big jobs we should see in the next 20 years involves engineering of roadways and highways, roadways, bridges, all of that good stuff. So lots of jobs in the engineering field for people that can do things like this. All right, away we go. We're going to write a polynomial function in factored form, because what we want to do is add that to our toolbox of things that we know about polynomials. Because right away, I can't help it. I look at this and I see x to the third, stuff behind it, going to look something like that. You know, once you know what to look for, it's hard not to. So it's going to look like that. But obviously, this one is going to cross the x-axis somewhere. Not exactly sure where, but it's going to cross the x-axis. And that's what factoring is going to help us with, is finding those. So we go back to all the things we did before. We look at it and say, can I take out a greatest common factor? Oh, I can't. There's next and all that stuff. The next step would be, is this a perfect square trinomial? Because remember, that's what we always check for second. Is this a perfect square something or other? And the answer is no, because negative 15 is not a perfect square. But that doesn't mean that I can't just good old-fashioned factor this thing. So I need two numbers that multiply to negative 15 and add to negative 2. What's going to do that? There it is. Now what I can add to my toolbox about this polynomial is this. Not only do I have the end behaviors, but I know it's going to cross the x-axis at 0, at 5, and at negative 30. And I could use that to get a much better graph of this function. In fact, I'm just going to make a quick sketch for you here. That's what I know right now. Here's what I know is going to happen because of the number of turning points. The only thing I don't know is how high to make this little hump right here and how low to make that one. And that's what we need the graphing calculator for at this stage of the game. Is how can we get that piece to happen? But the rest of it, we can do. We're totally capable of doing that. So got it, number 1 says, what is the factored form of x cubed minus x squared minus 12x? Start through the list. Is there a greatest common factor? What is it? Let's take it out. Is that a perfect square trinomial? No. You know, the first term and the last term have to be perfect squares for that to happen. That ain't happening. Doesn't mean we can't factor it, though. We might be able to find two binomials. So what would make this work? Jackson, you got it again? Thought you had it. Then it was done. 3 and negative 4. There it is. So this one, definitely going to cross at 0, 0, negative 3, 0, and 4, 0. Those would be the spots where this graph is crossing that axis. So all of those pieces come together. Let's just try drives me nuts that we have to use the graphing calculator for those local maxes and mins. You know, it's just, you have to know calculus to do it, and we're just not there yet. So, roots, zeros, and x-intercepts, it's the same math. You're just explaining something different. So what we do is say, if p of x equals a sub n, x to the n plus a sub n minus 1, that really is a scary looking thing. All that means is a polynomial in standard form. If you look at it, you'll see it's x to the n, then they subtracted 1, then they're going to subtract 2, 3, etc. until they get down to x to the first. So it's the same thing we've been doing. And this a sub n minus 1, the leading coefficient, the next coefficient, the next coefficient. So x minus b is the linear factor. Those are the factors that we just did. Why is it called linear? Because we had x to the first in all of those. So those are linear factors. B is a 0 of the polynomial function. So when we factor it and we take that another step and say, let's find the zeros, what we're really doing is we're finding the x-intercepts of the graph. Where's it going to cross the x-axis? And then the third one, seems kind of weird that it's even stuck in here, but b is a root. This we did in chapter 4. Where we said, hey, if we could solve something like that, we're finding the roots. So finding the roots is still solving it. You know, it's, we could set x squared equals 4 to x squared minus 4 equals 0, and then we're solving it. So all of those things really are synonymous. We're finding the solutions, we're finding the roots, we're finding the zeros, we're finding the linear factors and the x-intercepts. You just have to know what to do and what they're for. So that's the good piece. Alrighty, this one says, what are the zeros of x plus 2, x minus 3, x minus 1, x minus 3? And graph the function. Well, it's not hard to do, except I'm going to take you away from a step that's going to show a little maturity in your math right now. And that would be, we're not going to write it that way anymore. Here's why. That's a great baby step to get you where you need to go to figure out what these are going to do. But it's actually wrong. So we've accepted it up to this point because, you know, we wanted to make sure we were focusing on the right topics. But the right topic now is graphing accurately. This is a line. If we say x equals -2, we're telling people that there's a line that's going to cross this. That's not what we're saying. We're saying the point -2, 0 is going to be on this graph. So from now on, when we write our zeros, we're going to write those as x-intercepts. Make sure we give it as a point where it's going to cross that axis, because this is talking about graphing. When you're talking about graphing, you want to know what are the points where this is going to cross. 1, 0, and 3, 0. So, I also try to put this together with what I know about leading coefficients and degrees. So I look at this and I think, okay, so my first term would be x times x times x. That's going to be x cubed, and I get that little sketch in my head right there. So now, I can put my -2, 0 on here, 1, 0, and 3, 0, along with end behavior. And then I'm just going to take a guess at what's going to go on. Now, my guess comes from the fact that if I multiplied all of that together, there's going to be an x to the third, then there's going to be an x squared something, an x something, and those x's are going to distinguish this middle behavior. So my guess is I'm going to do something like that. Has to. Because that's the only way I get the end behavior and the zeros that I need. But we do have to grab the graphing calculator, because we don't know exactly where yet. And like I said, it's going to take a little calculus for us to get that. So we're going to put it in parentheses and all. We won't even bother multiplying all that out. So parentheses x plus 2, parentheses, parentheses, x minus 1, parentheses, parentheses, x minus 3, parentheses. A little zoom 6 action. look like I'm too far off, but we want to know exactly where those points need to go. So that would mean blinky time. Second trace, number 4, I'll go after this max first. Getting on either side of the hill and pressing enter. So local max of 8.2 at negative 0.8. So let's see, negative 0.8, 8.2, yeah, I was off there. And then we need that local min. So second trace, number 3, blinking on the left side of the valley, right side of the valley, and enter your guess. So that will be a local min of negative 4.1 at 2.1. So 2.1, 1, 2, 3, 4, and a little bit more. And we've got it. So still some dependence on the graphing calculator at this point, but it's a pretty big deal that we can get the rest of that.
So what are you punching from?
Oh, second trace. And then the max would be number 4. And you make sure you get blinky on the left side of the hill coming down. And press enter. And then right arrow until you get to the right side of the hill and press enter. And enter your guess. And then you do the same thing, but think of it as a valley for the min. Local min. All right. So far so good. Let's just stop right now. I mean, if this is all we were doing today, where we're factoring to find the zeros and stuff, how would you feel? 4, 3, 2, 1, 0. So I can see. Okay, and this is where it's the difference between people that are really confident about their factoring, and then there's also the people that aren't necessarily confident with the graphing calculator. We do have to get good with the graphing calculator as far as those local maxes and mins go. So those numbers tell me you're not feeling ready to be on your own yet. So let's keep going. This says, what are the zeros of y equals x, parentheses x minus 3, parentheses x plus 5, and graph it? Well, if this is 0, we have a 0. So there's my first x-intercept. It's at 0, 0. This one would be a 3. So 3, 0. And the last one would be a negative 5, 0. But now I need that overall picture. What's the degree of this polynomial when it's all multiplied out? X to the third. Is there any possibility there's going to be a negative in front of that x to the third? No way. None of those x's are negative. So end behavior should look like that. So we get our zeros on here. And you remember, end behavior is going to go here and here. But again, we'd just be guessing. I mean, we know this is going to happen again. We just don't know how far. So it is graphing calculator time. Oops. Doesn't look like I'm going to be able to go by ones on my y's. And that's okay. Now's a good time to find that out. So I need more up and I need more down. That's my y values. So maybe I'll try negative 20 to 50. Ah, there we are. So what I want to do is find probably the highest point, because that'll tell me what I should really do for my intervals. So second trace, number 4, and put blinky to work. And we get negative 336. So local max of 36 at x equals, well, actually, I'll just put at negative 3. You could put at x equals negative 3 if you want. All right. Well, I only have 10 of these little buggers. We could go by 4s, and we would fit it on there, but 4s are kind of awkward. So I think probably going by 5s, just for the y's, would be a good idea. So we have negative 3, 1, 2, 3, and 5, 10, 15, 20, 25, 30, 35, a little bit more. That's what the graphing calculator is for. Now we need to know how low this one's going to go over here. So answer the question, how low can it go? Second trace, number 3. Left side of the valley, right arrow, right side of the valley, enter guess. That one's not so perfect. So local min of negative 14.8 at 1.7. So remember we went by 5s here on the y-axis. 1.7, 5, 10, 15, so not quite that far. That one I was pretty close with my guess on. So you can see how, even just one number to show me an interval can make a big difference on a test. Because I have to know, what did you go by when you went to do this graph? And then this information really has to be good. That local max and that local min, so we can see where those turning points occur. Where are they at? So we went from factoring to applying this, and we're going to keep talking about applying this wonderful stuff. Now we get to the factor here. Because if you looked at those last two and said, hey, they factored it for us, you've got to know that is not going to happen most of the time. And most of the time, we're going to have to factor that so we can see where those zeros are. So the expression x minus a is a factor of a polynomial if and only if the value a is a 0 of the related polynomial function. And that's what makes it so important for us to be able to work this forwards and backwards. Because like I said, I want you guys to be able to go into computer programming and say, got this. Computers speak math. I know math. So we look at this and we say, how did they get those for the zeros? Well, in order for this to come out to be a negative 2, it had to be plus 2. How did they get themselves a 2? Well, from x minus 2. How did they get a 3? From x minus 3. So this is all about, and they switched it up now, they're using x minus a. They don't want to keep talking about h, because h has to do with the vertex, and they don't want us to mingle those two topics together. But you can think of it that way, because it's always the opposite of what we see. And then this says a cubic polynomial function, so we can't just leave it like this. We need to name it a function, f of x, g of x, h of x, whatever it is. And if a person knows basic math, we have to make it obvious that this is a cubic polynomial function. As it sits right now, that would not be obvious to like an exponential algebra student. They wouldn't know that. So we are going to go ahead and multiply this out. The key to that is finding even 2 of these that will make the multiplication a little bit easier. So with this one, I would definitely multiply those 2 together first, because that's the sum and difference pattern, and that's going to come out very nicely into x squared minus 4. And then we can just do FOIL, and we can get the rest of this. So we would have x to the 3rd minus 3x squared minus 4x plus 12. Obviously a cubic, and we see the 3rd degree immediately in the front in standard form. And it is a polynomial function because we have our little f of x. So far, so good. Now, this one gets a little interesting. What is a quartic polynomial function? So think about what that means. And we have -2, -2, 2, and 3. Ouch, now it's getting bigger. So f of x equals x plus 2, x plus 2, x minus 2, and x minus 3. Lots of ways to group this one as well. Some of you might look at this and say, oh, I remember x plus 2, the quantity squared. I'll just do that part right away. It does work a little nicer if we're constantly trying to put those sum and difference patterns together, and that's because you eliminate that middle term. It makes things a little easier. So I'm going to go ahead and do that math first. And then I would probably just multiply the back two together. That's some basic FOIL there with some small numbers. And then we have to figure out how do you multiply that binomial times a trinomial. And a couple of years ago I had asked students, what's some kind of mnemonic device that you could tell people, you have a binomial times a trinomial, what could you do? And one of my students said, well, it's a clamshell. You take this times this times this, and this times this times this. Makes perfect sense. It's a clamshell. So we multiply everything in the second set of parentheses by x squared. And then we multiply everything in the second set of parentheses by -4. And then you just combine any like terms that you can. Just the x squared terms that we put together. That's a monster. But is it a quartic polynomial? Yeah. And you know what? If you're going to do all of that math and take the time to do this, you probably want to see it so you can know, hey, this is doing what it's supposed to do. It's supposed to cross the x-axis here, there. So x to the 4th minus x to the 3rd minus 10x squared plus 4x plus 24. Oh, boy, baby, better hit zoom 6 once it's done here. Now, that's not a bad look. We can still see the zeros. Now, remember, if we see a 0 twice, that means it hits and bounces off. That's a tangent. So we were supposed to have that hit at -2 and bounce off. And then it goes right through 2 and 3, which is exactly what it's supposed to do. So does that guarantee our polynomial is right? No, because, it's still those local mins and local maxes. That we're just basically throwing a dart, for those. We don't know. But the rest of this was what they wanted us to do, and we have that. That information is there. So now it says, let's go back and look at these. Let's graph them and see what they look like. So let's get those on there. And our first one was x to the 3rd minus 3x squared minus 4x plus 12. The zeros were at -2, 2, and 3. Well, that makes sense, what we're seeing there. So we probably want to do our second trace number 4. See what intervals we can go by. And notice I didn't even change my window yet, because that's what I really needed to see. So it's going to go up to 13. So if we go by 2s, it'll be just fine. So let's see, we are at negative about a half, 2, 4, 6, 8, 10, 12, about there. And then we have a little dip below 0 for our minimum. So 2.5, negative 1.1. I wish I hadn't cleared the other one. X to the 4th minus x to the 3rd minus 10x squared plus 4x plus 24. Now with this one, hopefully you could look at it and say, oh, yep, it's going to be all the way up at 0.24. Because if we put zeros in for all of the x's here, 0, 0, 0, 0 plus 24. And that's going to be our highest point. So let's see, 24. Let's go by 3s. Usually I'd say let's just go by 5s and get it over with, but let's go by 3s. So 0, 24. 3, 6, 9, 12, 15, 18, 21, 24. And we had a repeater 0 at negative 2. And behavior. But now, it could be that 0 and 24 is not the highest point, so we better take a quick look at that. And knowing that 0, 24 is going to help me figure out what to put in for my highest y value, I just put 30 in there just to make sure. And it does look like that's the highest value, so looks pretty good up there. Next thing to do would be put those other zeros on there, which were 2 and 3. And then find our little local min over there. So about 2.5, negative 5.1. And we went by 3s. I kept thinking, why do we have so much time in first sergeant? They had like 3 homework problems they asked about before we went on anymore. Because they had subs the last 2 days. I had technology training yesterday morning. So what they want to know is, how do they differ and how are they the same? Let's go after how they're the same first. You notice anything that's alike in these two? Anything we had to do that we did twice? The zeros. Yeah, I mean they had negative 2, 2, and 3 as the zeros. So similar. Are there zeros? But they're definitely different, right? So what's different about them? There's several things. So what's the big deal there? What's the change when you go from quartic to cubic? So, even the shape of the graph. You see how we could be here all day kind of doing this, because they're so different. So the basic shape is different. The end behavior is different. Do they have the same turning points? The turning points are different. So there's a lot of things about them that were different. What they had in common were those zeros. That was what they had in common. And I am going to stop there because that's the place we got to in first hour. So that way everybody will be at the same place. All right, I know it's a lot, but I need to see your 43210. How you feel about starting to put all the polynomial description stuff together? Okay, the numbers are looking a lot better since I last asked. All right, that's good. And a little practice will definitely help. There's some practice.